In this section, we're going to look at a new system for graphing points and functions or equations. And this is called the polar coordinate system. And we need trigonometry to graph in this system, as we'll see. So this system is based on we have an origin, O here, and if we draw a ray, then we can rotate about the origin in either direction, and that will generate an angle, which we're going to call theta. So this is the same setup as we've been using. If we rotate in a counterclockwise direction, theta is positive. A clockwise direction, theta will be negative. I should mention here the origin is also called the pole in this system. And so a point in the polar coordinate system is based on this angle theta and then a radius r. And the point is denoted in this order. R is first and then theta is second. So r theta. And r is the distance from the pole to the origin. I said that wrong, sorry. I haven't had enough coffee yet. From the pole to, you count from the pole and out. So if r is positive, you go along the direction of theta, and if r is negative, you go actually the opposite of theta, as we'll see. So r can be positive or negative. What that means then is, unlike the rectangular coordinate system where each point has a unique coordinate that represents it, every point in the coordinate system can be represented in an infinite number of ways. Well, except for the origin. The origin would just be 0, 0, of course. But otherwise we can, change the angle. We can change r from positive to negative. So let's look at examples here. So we have the point 1, 3 pi over 4. So it's a little odd because r is first and theta is second, but you're actually going to use theta first. So 3 pi over 4 is over here, of course. And then notice in this system, it looks like the x and y axis, and you can actually think about the two systems superimposed upon each other. We can still refer to this first, second, third, fourth quadrant. But this is our pole, and this is our positive, x-axis, but that's our ray that we are rotating around. So 3 pi over 4, just as we usually would be right here. And we go 1 unit out. So the polar system often has these circles to help you count the correct number of units from the pole. So this is the point. So this is 1 unit. 1, 3 pi over 4. Negative pi over 6. So these lines here represent our pi over 6 of way to pi. So negative pi over 6 is here. And then we go count 3 units. 1, 2, 3. So this is 3 negative pi over 6. And then 3 pi would be over here, right? 2, 3. But then we go negative 4. So even though 3 pi is this way, we're going to count back because r is negative. And of course, negative 4, 3 pi is equivalent to, we could do theta is 0, and then r would be 4, or we could do 2 pi 4, we could do pi. Let's see, I told you I didn't have enough coffee yet. I'm mixing these up. I don't know why I did that. I need an eraser. R goes first, even though you think of the angle first. That's kind of awkward. So 4, 0, 4, 2 pi, negative 4 pi. Right, so we go pi and then back 4. 0 and then count out 4. So this is why there's an infinite number of ways to represent the point, because you can keep circling around and either go 4 or -4 depending on whether you have an odd or an even multiple of pi. And you could show that with any of these points. Okay, so let's look at the next page. So this one says find two other polar coordinate representations of 5 pi over 6. So I don't have the coordinate system here, but 5 pi over 6 would be here. So we could just go out 5, right? That's the point we're talking about. But we could also go -7 pi over 6, 5 would be one possibility. And that would work for the first one. So for r greater than 0, we could do 5 -7 pi over 6. For r less than 0, so we're talking about here, right? I'll put the point here. This point. So we could also just go down pi over 6 and then back 5, -5, -pi over 6 would be an answer that would work for that. And of course, answers are not unique. There are other possibilities here. All right, now I talked about superimposing the xy plane onto the polar plane. And if we do that, we can think about the coordinates in polar form or in rectangular form. So like this point here is -4, 3 pi, but that's just in rectangular form. X is 4, y is 0. So that's what we want to look at here. If this is x and y, then we go over x up y, right? And this should be a theta. It looks like a 0. R theta. It's really tiny, but I don't know if I have a typo or maybe it just didn't print right. So to convert back and forth, if we know what x is and we know what y is, right? So say we know x and y, then, and this is theta, and this is r, we can just use trigonometry to derive formulas to convert back and forth between the two. So it depends, do we know r and theta or do we know x and y? If we know r and theta, we should be able to find x and y. And if we know x and y, we should be able to find r and theta. And so of course, the coordinates of these points here, x, y, we've derived this before. X is equal to r cosine theta, and y is equal to r sine theta. Right? The cosine of theta is x over r, and the sine of theta is y over r. We've done that before many times. So just solve those for x or y. So this first set of formulas, this is if we know r and theta. So we're given the polar coordinate, we convert to rectangular in that case. In the other situation, we know x and y. And we solve for r and theta. So of course, the tangent of theta is y over x. We could use that to solve for theta. Now you have to be mindful of we're using tangent inverse, that we might need to make an adjustment to get in the right quadrant, right? Because tangent inverse is only going to give us an answer in quadrant 1 or quadrant 4, -pi over 2 to pi over 2. So make sure you get theta in the right quadrant. And then r, of course, is, just use the Pythagorean theorem, r is x squared plus y squared. And solve that for r. And r can be positive or negative. You just have to make sure you're getting the right theta that corresponds with that. So let's apply both sets here of formulas. If we want rectangular coordinates, and these are in polar points, right? pi over 2. First we need to find x. X is r cosine theta, so negative 5 cosine of negative pi over 2. Cosine of negative pi over 2 is 0, so this is equal to 0. Y equals negative 5 sine of negative pi over 2. So negative 5 times negative 1, which is 5. So the rectangular form, let's call this A for part A, is 0, 5. So think about that. That should make sense, hopefully. If you go down to pi over 2 and then back 5, you're on the positive y-axis. That's in rectangular form. Just x is 0, y is 5. So we can convert back and forth between the two systems. All right, in B, let's call this B. In B, x equals 4 cosine of 4 pi over 3. That's quadrant 3. Cosine is negative, right? So 4 times negative 1/2, which is negative 2. Y equals 4 sine of 4 pi over 3. Sine is also negative in quadrant 3, and square root of 3 over 2 if the reference angle is pi over 3. So negative 2 square root of 2. So the rectangular form is negative 2 square root of 2. So we're talking 4 pi over 3, 1, 2, 3, go out 4. That's the same as going back 2, down 2 times the square root of 2. Whoops, except it's here, right, at pi over 3, not pi over 6. So, like here. That makes more sense. This number's bigger than this. So, wait, 1, 2, 3, 4 is about here. See how it lines up with 2? And then this would be negative 2 square root of 2. All right, moving on. Now we're going to go the other way. So we converted from polar to rectangular. Now let's convert, rectangular to polar. So these are just the usual ordered pairs that you're used to seeing. You know, negative 5, 5. That's in quadrant 2. So first we need to find, well, it doesn't really matter which one we find first, but let's find r first. So for A, r squared is negative 5 squared plus 5 squared. And of course, you're going to take the square root. This is basically the same formula that you use to find the modulus of a complex number, right? There's a lot of similarities with converting a complex number to rectangular form and converting rectangular coordinate to rectangular form or polar form. Make sure you don't confuse the two ideas, right? Excuse me. This is just our usual graphing of ordered pairs. In the last section, those were complex numbers. Those aren't ordered pairs. Okay, so 25 plus 25 is 50, so r is the square root of 50, which is 5 radical 2. And then theta, if x and y are the same in absolute value, then you should know you're on a multiple of pi over 4. And in quadrant 3, it's 3 pi over 4. You shouldn't even need the formula for that one. But of course, if you did use it, tangent of theta is y over x is negative 1, right? And that's in quadrant. You have to think about the quadrant in quadrant 2 so that you get 3 pi over 4. Okay, so our polar point is r is 5 square root of 2, theta is 3 pi over 4. So that's for A. For B, so again, r squared is x squared plus y squared. I'll just take the square root of that right away. So square root of 3 squared is 3, negative 3 squared is 9, square root of 12, which is 2 radical 3. And then tangent of theta is negative 3y over x. So negative 3 over the square root of 3, or negative 3 square root of 3 over 3, which is negative square root of 3. So that means the reference angle is pi over 3. And then, of course, tangent is negative in 2 different quadrants. You need to think about what quadrant this one is in, right? Is it quadrant 2 or 4? Well, this is quadrant 4. So in quadrant 4, theta equals 11, or, sorry, I almost did pi over 6. It's pi over 3, so 5 pi over 3. And so the polar point is 2 square root of 3, 5 pi over 3. I don't know why I didn't leave more room for this problem. Well, the next one is a quick one because it's on the y-axis, right? 0, and then x is 0, y is negative 4, so you would just go down 4 units. So you don't need a formula for that. You know r is 4. You can use negative 4, but I'm going to use positive. And then theta would have to be, you can do 3 pi over 2, or you could do negative pi over 2. So we've got 4, 3 pi over 2. This is B, C. So, you know, you don't always have to straight go with the formula. Use some, you know, use your common sense and think about where the point is. All right, so now we're going to look at polar equations. And polar equations involve r and theta, but of course you don't need to have r or theta in the equation. It could just have r, it could just have theta. Just like when we graph using x and y, right? You could have y equals 3x plus 1, or you could just have y equals 1. So it can involve one or both of the variables. If they do have both r and theta, we like to write r as a function of theta. So theta is the input, and then we solve for r. I mean, that should make sense because the trig functions would operate on theta, right? If we put theta in terms of r, then we have to use inverse functions. Okay, oh, excuse me. It's really early and I'm not awake yet. All right, so we're going to convert these to polar form. They are in rectangular form. And so all we need to do is use the formulas for x and y that we derived. Wait, where's my... Right here, x is r cosine theta, y is r sine theta. We want to get out the x's and the y's, replace everything in terms of r and theta. So this first one will be 2 times r cosine theta, and you can drop the parentheses, plus r sine theta equals 4. Again, the parentheses don't really need to be there. So we like to write r in terms of theta. So factor out r, and you have 2 cosine theta plus sine theta equals 4. So r equals 4 over 2 cosine theta plus sine theta. So this is a line, of course, right? So this line in rectangular form, this is a line in polar form. And we won't graph this one by hand. We're going to graph some equations by hand, but not this one. But we could put this in our graphing calculator. I'm going to show you a little bit later how to graph polar equations on the graphing calculator. And if I remember, we'll come back to this one, but you could come back to this one on your own once you know how to do it and plug it in, and you'll see that you get a line. Okay, this one here we have in rectangular form. Hopefully you recognize that's a circle. It's a circle centered at 0, 4 of radius 4. So doing the same thing we did over here, x is r cosine theta, so we're going to have to square that. And then y is r sine theta. So square both of these, r squared cosine squared theta plus, and then this you have to distribute, so you're foiling, if you will, taking this times itself. Okay, so we could just leave it like this, but we want to write r as a function of theta, so that's why I'm going further. So distribute r, oops, that should be minus 4. R sine theta times r sine theta is r squared sine squared theta. And then we'll get minus 4r sine theta on the inside product and on the outside product, so minus 8r sine theta. And then negative 4 times negative 4 is plus 16. Okay, so notice the 16 and the 16 here. We could subtract those and they cancel. And this part right here, we can simplify using the Pythagorean identity. If we factor the r squared out, cosine squared theta plus sine squared theta is 1. So I'm going to make that replacement. So now I'm down to r squared minus sine theta equals 0. And this is a factoring problem now because r is in both. We want to isolate r, so we got to factor out r. And we're left with r minus 8 sine theta equals 0. So r equals 0 or r equals 8 sine theta. So there's two equations. This is just the pole, r equals 0, because, or the origin, I mean. The, theta is not involved, so this is just the point 0, 0. And that point is actually part of this equation. Notice if theta is 0, r will be 0. So we can just simplify this to r equals 8 sine theta. If this point wasn't part of this, you'd have to include it. But since it's here, we can just simplify this to one equation. And so this 8 sine theta is the the same circle. So in polar form, notice how much simpler the equation is, right? So sometimes, especially like things with a lot of symmetry and curves, in polar form, they are simpler equations than they are in rectangular form, which later on down the road, when you take calculus, will make certain calculations a lot easier because you have a simpler equation or function. All right. Now we're going to go the other way, convert the polar equation to rectangular. So again, you need to use these equations that we derived, somehow getting either r squared or tangent theta in the equation so you can make these replacements. So r is 3. You could just replace, you could use a square root here, but you could also just say, well, that implies r squared is 9, square both sides, and then r squared is x squared plus y squared. Right, so if r is 3, think about this in polar form, we're talking about no matter what theta is, you would go out 3 units. And so you'd get a circle of radius 3 centered at the origin. And of course, that's exactly what x squared plus y squared equals 9 is. It's a circle centered at the origin of radius 3. So here's our equivalent equation in rectangular form. Again, you could have just put square root here and then squared both sides. It doesn't really matter. All right, when you have just theta and not a function of theta like these, then you want to bring in the tangent of theta. So you want to take the tangent of both sides. Whoops. Take tangent of both sides so that you can use this equation. So tangent of both sides, tangent of theta equals the tangent of pi over 3. And the tangent of theta is y over x then. So this is so we can use tangent of theta equals y over x. Let's move that over. So y over x equals the tangent of pi over 3. And of course that you should evaluate. It's the square root of 3. So this is y equals the square root of 3 times x. And that's a line with slope square root of 3. That shouldn't be a surprise that it's a line if you think about the theta equals pi over 3. Here you're saying let r be anything. Theta is always pi over 3. So you would get every point that exists on theta equals pi over 3, and those could be positive r's and negative r's, so you get that line. So this is also a line with a slope of square root of 3. Okay, C, because C has a function of theta, you're not going to use tangent here. We're going to do something else. And this one's a little tricky, but we still need to get x and y involved, so we can use either of these, but we can also use these. So notice there's no r here and no r here, but I can introduce an r by taking both sides times r, and when I do that I'll get r cosine theta here, r sine theta here, and this r squared, well, we can use this equation then. So take both sides times r. So we get r squared equals 6r cosine theta plus 2r sine theta. So r squared is x squared plus y squared. And r cosine theta is x, and r sine theta is y. All right, we're not going to be able to put that y as a function of x because it's not a function. This is a circle. You don't recognize that, which I know because I have an x squared term and a y squared term, and they both have the same coefficient, and then the x term and the y term just mean that this isn't centered at the origin. So if I wanted to know where this was centered, I could do some college algebra here. X squared minus 6x plus y squared minus 2y equals 0, and then complete the square on both of these. X squared minus 6x plus 9. I'm not going to spend a lot of time on this. It should be review. But remember, you take negative 6 divided by 2 is negative 3, and then square it. So you add negative 3 squared is 9. Negative 2 divided by 2 is negative 1. Square that, and you get 1, positive, of course. And then you have to add those numbers to the other side. So x minus 3 squared plus y minus 1 squared equals 10. So this is a center of 3, 1, and a radius of the square root of 10 for this circle. Okay, I'm going to pause the video here, take a break, and then we'll graph a couple of equations.